What's up, YouTube? This is Govin.
And we're about to explain the physics of centrifuge.
Let's go!
I threw my hands in the air and said, show me some of that. He said, if you dare, come a little closer. Round and around and around and around we go. Oh, now, tell me now, tell me now, tell me now.
Could you explain the ride's motion?
The ride spun the cart in a circle, and that small circle span in a larger circle.
The rotational motion really made me dizzy.
So I'm going to draw the car that we were sitting in when we rode the ride, and then the two dots represent me and Govin, and I'm the top dot and Govin's the bottom dot. And so the car had angular velocity in a small circle, and then the car also had translational velocity in a line tangent to the circle. Then this whole small circle spun in a larger circle. Alright, and then this bigger circle has angular velocity as well. This is also spinning. And then there's a certain point in time, say T2, when both me and Govin were much closer to each other, and the two dots are like pressed up against the outside of the car, because when you ride the ride you're pushed outside of your car, as you can see, and then the car is spinning in a small circle with angular velocity. There is also centripetal force acting both on the car, the small red car, and also centripetal force acting on the green small circle.
Did you two collide when you were sitting together in the ride?
Yeah, as the ride got faster, I started squishing Jack more and more.
Yeah, he squished me the whole time.
They ask you how you are, you just have to say that you're fine when you're not really fine, but you just can't get into it because they would never understand.
Now, this video is a demonstration of what Jack meant when Govin was squishing him on the ride. Now, it hasn't happened yet, but when they come around this time, you will see that Govin has shifted towards the outside of the car, and it's squishing Jack, as you can see there when they turned around.
Did you feel anything pushing or pulling you on the ride?
Yes, indeed. I felt something pushing me towards the outside of the little circle.
And why do you think that happened?
I think it happened because of our inertia. When we were traveling in a straight line and the centripetal force was pulling us towards the left and making us move in a circle, and because of that, our inertia was pulling us towards the outside of the car.
Do you think there were any other forces, like maybe gravitational force?
Oh yeah, when we would go down the incline, we would accelerate because of gravity.
As Jack and Govin explained, there are several forces that were present on the rider during the ride. Now there's mg pointing downwards, gravitational force, and there's a centripetal force pointing to the center of the circle. And lastly, there's a normal force that allows the rider to sit up on the ride against gravitational. Friction of the ride can be ignored due to the fact that the cars on the ride were slightly elevated and not touching the ground.
How fast did you think you were going when you were on the ride?
It felt really fast when the little cars were moving in the same direction as the big circle, and much slower when they were moving in opposite directions.
Yeah, you're just really fast.
And was the speed of the ride different when you saw it from the outside?
Yeah, it felt like it was moving a lot faster than it looked like it was.
This is the concept of relative motion. Now, when you're on the ride, you're unable to see how fast the other cars are going, so you feel as if you're going very, very fast. But when you see it from the outside, the other cars are also moving at the same speed as any other car, so it appears slower in comparison to the cars on the ride.
This is an incline, angled at angle theta. And this is a car on the incline with mg weight pointing downwards. Normal force mg cosine theta pointing perpendicular to the surface. This component of mg sine theta, of mg equal to mg sine theta, centripetal force pointing towards the middle of the circle, and the angle between mg sine theta and mv squared over r is theta, which makes mg sine theta a component of mv squared over r. For the velocity of our cars, setting mg sine theta equal to mv squared over r cosine theta, mass cancels out, and rearranging the equation, we get g times tangent theta times r is equal to velocity squared. Taking the square root, we get velocity equals tangent theta times g times r. Square root.
I hope you learned a lot about physics.
We hope you carry these lessons throughout your entire physics career.
Thank you
very much for watching, everyone. Right now we're about to head to the food places to get Dan his funnel cake.
I don't want it yet.
He doesn't want it just yet, so we're not going to go just yet, I guess.
No, I guess
We're
not.
going to be going to what?
Where are we
Mama?
going?
I don't know.
What are we
It's
doing?
that way.
Alright, we're going that way
Okay,
to
that
whatever Dan
way.
wants to do because he doesn't have an assigned adult now.
Yes, I am his assigned adult now because Julie left him. Yeah.
And then I was stuck with Roger, who's 17.
Not an adult.
And then even Roger left me. So.
Yeah. Damn.
Thumbs up.
Why would you do portrait?
Oh yeah, that! I'm gonna mess this video. No, but I'm getting a pencil.
I'm recording. It's okay. Yeah, nice. Nice.
Hey guys, we just got off the Patriot and kind of nauseous right now, so we're taking a little break. Momo's not with us right now. She's kind of with the other girls having some fun. Roger joined us. What? Say hi, Roger. I want to die. Oh, Dan's back from the arcade. We gotta say hi. You broke the air hockey thing?
The puck went in the thing and then it come out.
Damn. Nice. Nice.
No, it was still going. It still had like 3 minutes left. And it was 5-0.
Hello! We're on the carousel! Woo! Woo! Hey, Jess! It's a video. It's
What's your YouTube channel? This is our project.
I know.
Subscribe to my project, guys. Hit the link in the description.
Now just